Hello, everyone. We're moving on to Chapter 2, Section 2.4 in Statistical Methods for Rates and Proportions. So in this section, we're going to learn about the approximate inference for a single proportion and statistical inference that goes along with that. So we're going to be in the situation where we have two outcomes, success or failure. And if we were to look at the number of successes in a fixed number of trials, then we have a binomial distribution with the total number of trials being n and the probability of success being p. And remember from a previous section that this is the PDF for the binomial distribution. But if n is large, and we say large is relative if our NP and NQ is greater than or equal to 5, then using the central limit theorem, we can get the distribution for X and we can get the distribution for P, the sample proportion. Remember that X is the number of successes, P is the proportion of successes. So based on central limit theorem, we get that X follows approximately normal with a mean of NP and a standard error of square root NPQ. And P follows approximately normal with the expected value of P being P and the standard error of P being the square root of PQ over N. So when we do our hypothesis test, we want to write out the null and alternative hypotheses. We want to calculate the p-value, make a statistical decision, and state our conclusions in context of the problem. So if we want to test that the true proportion equals some hypothesized proportion, we can set up the null hypothesis to be p equals p naught. And then we have three choices for our alternative hypothesis. We could do a two-sided test where we say the true proportion is different than the hypothesized proportion. We can do a less than test. The true proportion is less than the hypothesized proportion, or we can do a greater than test. The true proportion is greater than the hypothesized proportion. So P is the true value from the population and P naught is the hypothesized proportion. Calculate our test statistic, we can standardize in the regular way where we find our test statistic by taking the absolute value of our sample statistic minus our hypothesized proportion, and we divide that by the standard error, P0, Q0 over N. Now, this -1 over 2N, this is our continuity correction, and we'll only use the continuity correction if it's smaller than the absolute value of the difference between the sample and the hypothesized proportion. From here, we can calculate the p-value, and you do this in the regular way where you find the probability of being as extreme or more extreme than the one in your sample, assuming the null hypothesis is true. So your p-value is really dependent on what you chose as your alternative hypothesis. So if you have a two-sided test, you're going to get the probability of being in each of the tails. If you have a less than test, you're going to find the probability of being beyond your test statistic on the lower side of the distribution. And if you have a greater than test, you're going to find the probability of observing a test statistic of observing a value greater than your test statistic, or you're going to find the area in the upper tail of the distribution. And we're going to use that p-value to make a statistical decision and interpret in context of the problem. Just a note about p-values, and I think we've talked about this before, is that they're not an end-all be-all. They are the amount of evidence. So if we get a p-value of 0.045 or a p-value of 0.055, there's nothing magical about 0.05. We just have a little bit more evidence. But p-values are nice just to give us an idea of like, okay, where are we going to make this decision at? But don't put too much into when you're very close to the border of the rejection region. Okay, so if we want to calculate the confidence interval, especially if P is close to 0 or 1, you can use the formula in the book for PL or PU. Okay, and here's the formulas. And there's A lot of notation here, but once you plug this into R, it's going to be actually quite easy to get because we know our sample size, we know our sample proportion. We can figure out our Z alpha over 2 value. We know Q. So this is really just plug and chug, get through all the math. Okay. Here, P is if your sample proportion is between 0.3 and 0.7 and you have a large sample size, then you can use the approximation for your confidence interval. So you have P minus your critical value times the square root of PQ over N. And then remember, we have this continuity correction, or you can have P plus the critical value times the square root PQ over N plus the continuity correction. So when you use one versus the other, in practice, you could always use PL and PU, but PL and PU are a lot more complicated than the approximation that we see here. So people tend to like something that's easy. They give you similar answers. So this formula is a lot more straightforward, but in practice, now that we have computing, it doesn't really matter quite as much. So these approximations made it easier to calculate this by hand, but by computer, it's not terribly easier or harder to use either formula. And that is it for 2.4. We're also going to be doing some R code on this, so I look forward to seeing you in the next video. Have a great day.